All right, today we're going to talk about the arc elasticity for the demand or the supply. By the way, previous video we talked about only the demand side, and we had some issues with the signs because things would turn out to be negative. A very formal treatment of the elasticity would mean that the elasticity for demand would always be a negative number, but usually we just care about the absolute value of the number. That's why we added that negative to the formulation with the point elasticity. However, a formal treatment would not do that negative sign, and simply the elasticity for the demand curve would be negative, for the supply curve would be positive. But nonetheless, we'll adopt the more economic conventions rather than the mathematical approach. But there was another thing that we did whenever we talked about our elasticity, and it was the fact that we said it was going to be the percentual change in our demand, or it could be also supply, divided by the percentual change of the price. Well, I gotta change that into a P. 1 second. And we will write P. This is partly the reason why I skip the erasing, because it takes a minute to erase these chalk markers. Anyhow, whenever we did this and we did examples, we said, well, if we increase the price by a 10%, and that was my example, and the demand increased by a 20%, well, we're actually, if we have our demand curve, sort of like what we drew in the previous video, something like this. When you're talking about an increase in price, you're implicitly taking this first price, say price 1, and the corresponding demand 1 as your base point. So when you compute this, you're saying, well, I'm going from a price 1 to a price 2, and my demand is going from Q1 to Q2. And so what we normally are doing in this case is saying, well, I'm taking the delta Q, so I'm saying Q2 minus Q1. This will give you the negative value for the elasticity. And then you're going to be dividing by a value of Q. And normally what you're doing is you're grabbing the Q1 if you're talking about increasing a price. And if you're talking about decreasing a price, you'd be taking Q2. And but that gives you a definition that it is not symmetric. And the same thing would happen for the price, of course. All right, and that is not symmetric. So the idea of the arc elasticity is to symmetrize this. So instead of dividing by Q and 1 and P1, or just taking one base value, what you're going to be doing is you're going to be using the average between those prices. You're going to do P1 plus P2 over 2. And here you're going to be using, and I'm going to write it over here, Q1 plus Q2 over 2. And that then gives you a formula for the arc elasticity that would be equal to, and by the way, I'm going to write it as Q2 minus Q1. This would give you a negative value, but if you want to do it in terms of the economic context, you would just ignore the negative value. But in a sense, it is a little bit off from what we did in the previous video, because in the previous video, we put a negative in front of the derivative sign to force that elasticity to be positive. Anyhow, we have Q2 minus Q1. I'm going to keep this one over here, P2 minus P1. This is going to essentially be my, I'm not done, but this is going to be essentially your delta Q. And this right here will be your delta P. And remember that in our first formulation, or for the elasticity, point elasticity rather, then we said times P over Q, right? So we did the opposite. But in this case, I had a P1 plus P2 over Q1 plus Q2. And you'll say, well, what happens to your averages? What happened to the means? What happened to the twos? Well, the twos are appearing in both They're going to divide both quantities. So essentially they will end up canceling, and you end up with this formula. And this formula is going to be called the arc elasticity. And in a sense, it is much easier to compute. And this pains me because this is a calculus class. So technically I should tell you, oh yeah, the derivative approach, the point elasticity is way better. But this is something that you can actually compute with just 2 data points. So you could actually get a number for elasticity just with knowing what was the demand at certain price level and what is the demand at another price level. So you need 2 points, and that will give you enough data to compute your arc elasticity. There was another thing I wanted to say about the arc elasticity. Yes, this one is essentially this quantity right here is the slope of the secant line. So if you connect these 2 points with a straight line, the slope of that line is going to be that delta Q over delta P. So that gives you that right there. All right, so let's go ahead and give a silly example where we can compute some elasticity. And of course, it's going to come out to be negative, and that I think will be give us a good idea as to how to use it. So I want to leave the formula here. So I'm going to erase my graph, and I'm going to just give you 2 points for some random commodity that we'll come up with. So I'll erase this and I'll be right back. All right, so let's say that for a certain commodity, for a price 1 of $20, let's say, the demand is 300 units. Of course, this is made up. Numbers would be much larger, I assume, if you're going to have some commodity that's worthwhile while computing this. But for the example's sake, let's say that now we increase our value to 20, or cost rather, or price for $22, but now our demand for the product drops to 280. So 20 less people in our very idealized example will want the product, provided that we increase the price. But this can be actually computed if you have data for different products. And for example, something you could compute is for eggs. Eggs change value often, and you can find data for the demand. And actually eggs are very, very inelastic. But it's very interesting because as time goes by, and this is another idea that one should explore, is elasticity we compute it as a function of the price. But it should also be considered as a function of time, because as prices increase and they're sticky and higher, people will actually start looking for options. And we saw that in the latest change of price of eggs, the increase in price. People at first just absorbed the cost, but later on, people started changing their breakfast habits, and then they started consuming less eggs. So that is something that elasticity should also be a function of time. Anyways, that's an extra point that just beside the point. Anyway, let's compute delta Q. Delta Q is going to be Q2 minus Q1. And as I said, you dropped 20 customers, or the demand dropped by 20. And now your delta P, 22 minus 20, is going to be $2. So you increase by $2, you drop by 20 people. Now I need to compute this quotient. So P1 plus P2 is equal to 20 plus 22, which is 42. The answer to, anyways, Q1 and Q2, when you add Q1 and Q2, you get 580. All right, and now what we're going to do is we're going to write everything here to compute the elasticity, and I barely have room. And I get delta Q, which is negative 20, over delta P, which is going to be 2. So this quotient gives me negative 10. As I said, the elasticity will be negative. If we'd be doing elasticity of supply, it would turn out to be positive. And then we have P1 plus P2, which is 42 over 580. And then at this point, we can compute. This is going to be negative 42 over 58. And I'll put that in my calculator and I'll be right back. My calculator meaning my phone, because I don't have anything here. So we'll compute it and we'll be right back. So it is going to be approximately negative 0.72. So not inelastic still, but not very, very inelastic. If you look at the list of commodities and the elasticities, for example, eggs is about 0.1, so very, very inelastic. Cigarettes, 0.3, so also very inelastic. Although that data point is very old, so I don't know if now it has changed a little bit. Things that are addictive usually tend to have very, very low elasticity, because people will, unfortunately, still fund their vices before they try to quit due to price. So it's harder to price somebody out whenever there's an addiction. Anyway, that's a point, that's beside the point, but it does reflect, it can be reflected in the numbers. All right, that's what I wanted to talk about with respect to arc elasticity. There's one more thing I wanted to mention. I had the graph, I erased it. Unfortunately, I want to have to draw everything again to tell you one tiny little snippet. I want to tell you that, and then we'll wrap the video up there. So let me erase real quick. I will draw the graph and we'll talk about it in 1 second. All right, so one last thing about the symmetry of the arc elasticity. The point elasticity that we computed using the differential is also very symmetric. Why? Because you're using eventually one single point and you're using the tangent line at that point. That's the quantity dq over dp that we computed. And then you're just using this point p comma q. So you're centering just at one single point. Therefore, there's no the situation that we had before where, well, which is your base point that you're computing the percent, that doesn't exist anymore, because you're simply using a single point. And if you want to make the sign be positive, you throw a negative in front. But that's the one thing I wanted to say, that the point elasticity also addresses the issue of lack of symmetry when you are anchoring your point. So arc elasticity, point elasticity are symmetric in a sense. Now, just straight up elasticity that you compute with 2 points and putting P over Q, choosing one of them, that will have a little bit of an issue there. Ultimately, you're just trying to get a point, an idea as to what the product is, or the commodity is elastic or inelastic. But these two methods of computing elasticity do address that concern. Anyway, that's all I had for you today. I've talked more than I expected for this video, but thank you for being on the other side. Thank you for watching, and I'll see you in the next one.